So let's now talk about electrons in a periodic potential. So we've studied the properties of the Bravais lattice. So the simplest assumption one can make about the ionic potential is that it has the same periodicity as that of the Bravais lattice. So if the ionic potential at a point vector r is u of r, then if you shift it by a Bravais lattice, which is capital R, then the lattice potential does not change. So that's the periodic potential, and just by introducing this periodicity, you can gain enormous information about the properties of a solid without actually considering what is this u of r. Without what is this u of r, considering what is this u of r. So we will now be working in the what is known as the nearly free electron approximation. That is, we are going to lift the conditions of the free electron approximation. In the free electron approximation, we said that there is no interaction between the electron and the ion. We are now going to remove that approximation, but only not fully, just a little bit. The details of that we will look at in the coming videos. But we will continue to work in the independent electron approximation. That is, we are still considering that one electron does not interact with other electrons. So that means that if to study a solid, all I need to do is study one electron. Then all the properties I'll just multiply by n, the total number of electrons. I will get the full property of the solid. That may not be the correct picture, but that is the solution that you have to do in the independent electron approximation. Sorry. So this would be the simple form of the Schrodinger equation. So in the free electron Hamiltonian, we have just added the periodic potential u of r. So from free electrons, we will now be looking at what are known as Bloch electrons after Felix Bloch. So the wave functions that satisfy that equation, Schrodinger equation, will now be called as Bloch functions or Bloch wave functions. So now we first introduce a translation operator Tr, so that a translation operator Tr operating on f of r gives you f of r plus a Bravais lattice vector. So you can simply follow this argument to see that if I want to operate Tr and on h psi, then the result is the same as operating h on Tr psi. So Tr and h commute, which means that I can choose any eigenfunctions or any wave functions that give me eigenvalues for one operator, let's say Tr, then I am guaranteed to get eigenvalues for the other operator h as well. So I can choose any eigenfunctions which suit my requirement and that satisfy the eigenvalue equation for the operator Tr. Let's say the eigenvalue for Tr is some C of r, and that same eigenfunction will give me an eigenvalue for the Hamiltonian, in this case the energy. That's one of the basic things that you studied in quantum mechanics, so I'm just using that. Now let's look at the properties of this operator Tr. So if I do successive operations, first Tr and then Tr prime, or rather first Tr prime and then Tr, I will get psi of r plus two Bravais lattice vectors, capital R and capital R prime. But the order of operation doesn't matter. I can operate first on Tr, then on Tr prime, and vice versa. It doesn't matter. And I can also write the product of the two operations as the sum of the operations. So Tr into Tr prime can be written as T of r plus r prime. And again, if you look at the eigenvalues, if I just follow this argument, I can see that the product of those two eigenvalues, C of r and C of r prime, is equal to the eigenvalue C of r plus r prime. That's simply because of the nature of the function that we took, that we have taken. So now given this, so suppose I say that I want to find out C of A1, where A1 is one of those primitive vectors of the Bravais lattice or the Dirac lattice, and so I can write the Bravais lattice vector as some n times A1. So then if I want to find out C of R for this R, that would simply be multiplying C of A1 n times, right? So that will be C of A to the power n. So, because of this operation, you just if you successively operate it again, it's just like multiplying the eigenvalue. So it's C of A1 to the power n. So now if I have the full form of the Bravais lattice vector, this should be vector R. I can now write C of R as this kind of a product where each of it is raised to the power n, and I can now choose each of those primitive lattice vectors as this form, exponent of 2 pi I xi, and that xi can be some number. We don't know what that is. It can be real or imaginary, but with some number. We will worry about what that number is presently. So if I choose this form for the primitive vectors, then I can write C of R as this, and this resembles a dot product, so I can write this as e power I k dot R, and this k can be written as x1 b1 plus x2 b2 plus x2 x3 b3. The b's are the reciprocal lattice primitive vectors. Those are primitive vectors in the reciprocal space, and the two primitive vectors obey this relationship as we had seen before. So I'm now trying to find out the nature of the x's. So now going back to this, so now I have a form for C of R. So C of R now gives me this e power I k dot R, where R is a Bravais lattice vector. So now I can write when I operate TR on psi, that's going to give me psi of R plus R, and that's going to give me an eigenvalue equation. But I now know the eigenvalue. C of R is now given by this, and I now put it there. Now this expression is called the Bloch's theorem. Now what is special about it that you have to give it a name? Now suppose I write the eigenfunctions for an electron in a periodic potential to be of this form. It is just u of r some function into the plane wave. The plane wave is basically the free electron expression. I'm now multiplying the free electron expression with some function u of r. I don't know what that u of r is. So now I can write when I shift this Bravais lattice vector, I will get this, and now I demand that that function u of r should also have the periodicity of the lattice potential. So it is also it should also obey the property of the Bravais lattice. So if that is also a periodic function, then u of r is going to be given by this. So I can rewrite this as this, and I can simply write u of r plus r is basically psi of r times e power I k dot r, which is what this equation is. So what does the Bloch's theorem say? The Bloch's theorem simply says that given a periodic potential, I can choose my eigenfunction to be a product of the standard plane wave times another function u of r, where u of r also has the same periodicity. Then such a function would give me eigenvalues for the translation operator, and therefore such a function would automatically give me eigenvalues for the Hamiltonian as well. So this kind of an eigenfunction is suitable for an electron in a periodic potential. So it's an amazing result, because it tells you that given the lattice periodicity, without even knowing what the form of the periodic potential is, you are able to derive a form of the eigenfunction. You are able to derive the form of the wave function as a product of the standard plane wave into some function which also has the periodicity of the lattice. That's called the Bloch's theorem, and that's a Bloch wave function. So let me say that again. Given this Hamiltonian, and given that the Hamiltonian is a periodic function of a Bravais lattice. You can choose your wave functions as a product of the plane wave times some function u of r, provided that u of r also has the same periodicity, and that's called the Bloch's theorem. It's an extraordinary result because it tells you that the plane wave form of the electrons of a free electron is retained even in a periodic potential. Even if you take a free electron, which is just e power I k dot r, and you put it into a periodic potential, then the basic form of the plane wave is still retained, just that you have another function u of r which also obeys the lattice periodicity. Now, in the case of the free electron discussion, we had studied what is known as the Born-von Karman boundary conditions for solving the free electron Schrodinger equation, and we said that this condition, boundary condition, essentially means that you consider a box of dimensions L. Then you say that at the instant where the electron leaves the box, the electronic wave function enters on the other end. That's a traveling wave boundary condition. Instead of a standard the standing wave boundary condition, we use a traveling wave condition, and that essentially means in all three dimensions z plus L, psi of z plus L is going to be psi of z, and so on cyclically in all three dimensions. Instead of this, now that you are having this was just for a box, but now we are having a lattice, and that lattice has got a primitive cell, and that primitive cell can be translated in all three dimensions. So we are going to rewrite this Born-von Karman boundary conditions as psi of r plus some integer times ai. That is ai is a1, a2 and a3. So I can have integers capital N1, capital N2 and capital N3. So the Born-von Karman boundary condition will hold good for 1 unit cell in one direction, 2 unit cells, 3 unit cells, and so on, over all three directions, a1, a2 and a3. And the total number of unit cells is basically the primitive cells. The total number of primitive cells is basically N1, N2 and N3. That's the modified form of the Born-von Karman boundary conditions. So given this, and given the expression for the Bloch theorem which we have just proved, I can now combine these two and write this psi of r plus ni ai, and I can write this, and this essentially is psi of r itself. You can just pause the video and write it down for a moment and see. If I combine these two, I should be able to write this, and that immediately gives me this condition. So this has to be 1. Please pause the video, write it down yourself and see. So now for this condition, I can now choose the vector k as given by this. I had already said that the b1, b2 and b3 are primitive vectors in the reciprocal space. Then I can rewrite the condition like this, and that means that the product xi ni has to be some integral value mi, and I can now rewrite the k itself. I can replace the x's by this, and I now have m1 by n1, m2 by n2 and m3 by n3. So this is the general form of the allowed Bloch vectors in the solid. So please recognize we are still dealing with plane waves, and these plane waves are placed on top of a periodic potential, and then if you do that, then the form of the wave vector would be this. That's what we have just shown. So now I can, given this, I can now derive the volume delta k in the k space per allowed value of k. So what is the volume occupied in k space for a single value of k? And that's just your delta k, which I can just take this and take the find the standard way to find the box product, as it's called, I think, and that will just be this. Now this is the volume of a reciprocal lattice primitive cell. So in the reciprocal space, a primitive cell will have this volume. So this volume is basically this is equal to n times delta k. So what does this mean? Now each k value occupies a volume delta k. If I multiply delta k by n into n, so n into delta k gives me the volume of the primitive cell in the reciprocal lattice. That means that the number of allowed wave vectors in the primitive cell of the reciprocal lattice is basically the number of primitive cell in the crystal, that is in the real lattice. The number of primitive cells in the Bravais lattice or real lattice or direct lattice is equal to the number of allowed wave vectors in the primitive cell of the reciprocal lattice. Or if I assume that there is one lattice site per primitive cell, then the number of allowed wave vectors in the primitive cell of the reciprocal lattice is nothing but the number of lattice sites in the crystal. And that's a very important result which we will keep applying later. And that follows because the volume of the reciprocal lattice primitive cell is basically n times the volume of one allowed value of k, which is delta k. N into delta k is the volume of the reciprocal lattice primitive cell, and n is nothing but the number of primitive cells in the crystal, or if I assume one lattice site per primitive cell, it's the number of lattice sites in the crystal. Now you can show this relationship. It's a very simple thing to show. There's a relationship between the volume of the primitive cell in the reciprocal lattice and the volume of the primitive cell in the Bravais lattice or the direct lattice to be given is this. So I can now rewrite delta k, which is given by this, as delta k is 2 pi cubed by b. So this primitive cell volume is basically this guy. Primitive cell volume into n is going to give me the total volume of the crystal, and this delta k is going to be just 2 pi whole cube by b, and this is the standard result you got in the free electron. So in the free electron case, you found out that 2 pi cubed by v is basically the volume occupied by each k value in the free electron result. This is also the same. You have got the same result in this case also. So now the next step would be to rewrite the Schrodinger equation in momentum space, and there are many benefits of doing that. The benefits will become clear in the coming classes, but let's start with rewriting the Schrodinger equation in momentum space first.